Besides microphones, the other type of transducer we use on a daily basis is the loudspeaker. Speakers work the same way mics do, only in reverse. The same types of microphone designs are also utilized in speakers, with the most common being the dynamic moving coil approach. Just like a dynamic microphone, a traditional moving coil loudspeaker design utilizes the principle of a coil moving in a magnetic field, only the signal flow is reversed. Once again, there's a permanent magnet and an assembly with a coil of wire wrapped around it. This is called the voice coil. The voice coil sits within the magnetic field of the speaker magnet. A wire connecting to the voice coil carries the audio signal from the amplifier. The voice coil assembly is attached to the speaker's diaphragm, the speaker cone, or dome, itself. When an incoming audio signal passes through the voice coil, it creates a magnetic field which interacts with the field of the permanent magnet. This causes the voice coil assembly and the attached speaker diaphragm to move back and forth as the polarity of the audio signal swings between positive and negative. Naturally, when the speaker moves, it displaces air molecules, creating compressions and rarefactions, forming an acoustic sound wave. Since the job here is to create an acoustic sound wave rather than just react to one, as with a mic, the speaker diaphragm is, naturally, much bigger and heavier to allow it to displace enough air to create a sound wave with significant amplitude. As most of you know, the majority of loudspeaker designs optimize this process by dividing the full frequency range into two or more smaller ranges. The low frequencies are handled by the larger assembly, the woofer, and the highs by the smaller one, the tweeter. The division of frequencies is usually handled by an internal circuit called a crossover. Although in larger modular speaker systems, like the kind often found in high-end concert sound systems, the crossover functions might be handled by external electronics. Typical crossover frequencies might be around 2 to 3 kHz or so, depending on the relative size of the woofer and tweeter chosen. Sometimes a separate mid-range driver, or two, is included as well, and it's become increasingly common to add a subwoofer, especially to compact systems with smaller woofers. The use of multiple elements allows the speaker to efficiently cover the full frequency range of hearing, although how low a given speaker's low frequency response extends will depend on the size of the woofer and the design of the cabinet. Most speakers roll off the lows somewhere between 80 Hz and 40 Hz, depending on woofer and cabinet size. In fact, speaker design always involves a trade-off between three elements: low frequency response, size, and efficiency. Efficiency is measured by how much sound pressure level a particular speaker model can put out, usually with 1 watt of amplifier power at a 3-foot distance. This spec will often appear on spec sheets as sensitivity. Higher sensitivity means you'll need less amplifier power to achieve a given listening level. The majority of studio monitors nowadays are powered speakers with separate amplifiers for the woofer and tweeter built in, so the sensitivity spec may not be as familiar to people as it once was, when they had to match the proper amp to their chosen speakers. But the trade-off still holds. If you want a speaker that can play loud and have deep bass response, it'll need a bigger woofer and a bigger cabinet. If you want a small loudspeaker that can play very loudly, you'll have to sacrifice some bass response. That's why subwoofers are often added to the typical compact console-top monitors that are so popular these days. I'll touch on that a bit more in the next chapter. Both the efficiency and the low-frequency response of a speaker are affected by the physical design of the cabinet. You may have run into terms like infinite baffle, folded horn, or ported speaker designs. The cabinet can reinforce and extend the bass response of the actual driver, and each of these uses a different approach to do that. Ported designs are popular because they can help to slightly extend the low-end limit without increasing size, but how much help the port provides will depend on placement. Again, more on that next time. While full-range speakers, like studio monitors, usually incorporate at least a two-way design, woofer and tweeter, some speakers use only a single driver. The speaker cabinets that are used for electric guitar and bass amps are most commonly a single speaker, an 8-inch, 10-inch, 12-inch, or 15-inch dynamic model, in either an open-backed or a closed-back cabinet. Since they have no high-frequency element, and the cabinet, especially open-back cabinets, may not help much with the low end, these speakers have a pronounced mid-rangey response. This contributes a great deal to the characteristic sound of electric guitar. Trying to amplify a full-range instrument, like acoustic piano or voice, through a guitar cabinet will result in a heavily colored response. However, this is still often done deliberately as an effect, to add some strong mid-range punch to what may be considered a bland tone. Dynamic moving coil designs are used in the vast majority of speakers intended for use in professional audio applications. But ribbon elements and electrostatic elements are also sometimes employed, most commonly for tweeters. Just as with their counterparts in microphone design, ribbon mics and condenser mics respectively, these designs may provide a somewhat clearer, more delicate high-frequency response. The most typical approach is to combine, say, a ribbon tweeter with a standard dynamic moving coil woofer. For example, the speaker company Adam offers a very popular range of studio monitors that incorporate ribbon tweeters. In the next tutorial, I'll touch on some practical aspects of loudspeaker use, like placement in the studio and the use of subwoofers.